the head of the Department of Light and Matter within the interdisciplinary faculty and leads the Competent Center for Mass Spectroscopy in the University of Rostock. Professor Zimmerman studied chemistry at Technical University of Munich and physics at Ludwig Maximilian University Munich and earned his PhD degree in physical and analytical chemistry from Technical University Munich. His primary research interests focused on the development of novel photo ionization mass spectrometry methods for online characterization of aerosols, process gases, and combustion emissions. His research spans interdisciplinary investigations into composition, atmospheric processing, toxicology, health and climate impacts of ambient aerosols, including emissions from vegetations, wildfires, traffic, and industrial activities. His work also has led to the co-founding of one company called Photo GmbH in 2009. Professor Zimmerman has published more than 400 scientific papers, and he has received multiple awards, including one honorary doctorate from University of Eastern Finland in 2022. Since 2026, he has been appointed as a distinguished professor of Eastern Finland for Mass Spectroscopy and Environmental Chemistry Department at the University of Eastern Finland. Please join me in welcoming Professor Ralf Zimmerman.
You make it? Good afternoon. It's an honor for me to be in this prestigious institute, and with some of the colleagues we had a web meeting already. Now it's my first time in Pune. And also thank you to the colleagues from Mars. So they have shown me today a little bit of the sites of Pune as well. Today we would like to discuss a little bit more on aerosols and health effects and climate effects. I will discuss two technologies for a measurement as well as a biological approach to look at the health impact of aerosols in the following about 1 hour I've planned. So please let me know if this timing is okay. Then I will continue. Good. So just where we are based actually, let me see if I have a laser here. So yeah, we are based in Rostock, which is in Germany, in the north on the Baltic Sea, and it's a quite old university. We were founded in 1419. It's one of the oldest universities in Germany, and the oldest in North Europe, in the Northern Europe region. And it's a comprehensive university. We still have a working group in Munich, but the majority of the people are working as a group leaders in my chair, now moving more towards the climate. And the health aspect, always when I'm coming to India or China and see the air pollution here, it becomes that health still is a very important issue. And I think the start of everything was a smog event in 1952. So it was a severe smog event. There was an inversion situation in the atmosphere, and all the coal emission, everything piled up and it came out that the daily death record in Greater London was actually skyrocketing during these days of bad air pollution. And it took quite long, even after fresh air came in from the ocean. Okay, maybe I can also go closer. Okay, switch it off. Okay, very short change of microphones. Hello, is this better? Yeah, okay, good. Okay, now we have this very strong increase in a daily death rate here, and this led to a huge amount of studies. I always cite this one here, the Harvard Six City study, where the air pollution in different cities in the US is actually associated with the relative risk of premature death. And it's a quite nice correlation. In the following, this was investigated by thousands of studies, and now we can look to meta-studies. And if we now look onto the risk factors for a premature death, we see that lifestyle-associated things like smoking or wrong nutrition is, of course, still dominant. But from the environmental side, actually, air pollution is the most important factor. And this brings the World Health Organization to the conclusion that about 7 million extra deaths are due to air pollution per year. And if we now look to different studies, just to put this in perspective, we can see these are this World Health Organization, but they're different studies and authors, and it's all around that. Either so, for example, Lilly felt they have a stronger. They believe that the household air pollution is more important than the ambient air pollution, but these are all factors. We are discussing about several million excess deaths per year, which is more than we had annually in COVID due to COVID. So it's just that what normally is there from air pollution. And all this is relatively consistent over different studies. Why is it so? Well, in principle, it's easy to understand. We have fine particles which are able to penetrate in the deeper lung. There, actually, we have a sponge-like structure of the lung, which has only two cell lines, epithelium and endothelium, between the airspace and actually the interior of the body, so the blood vessels. And their particles and also gases could come in direct contact with the human body. It's the only place. Our skin, for example, is in principle dead. But in the air exchange region, there's a direct contact of the outer world with our body, and it's 80 square meters of surface. It's a huge surface which is in contact, which is needed for gas exchange. And this makes it so difficult. And you can see here that the small particles are actually relatively important for this aspect. And if we now look at the causes, there is quite something known about it. It's known that these particles are causing something like a chronic inflammation, which is driven by oxidative stress. So this inflammation changes the physiology of the lungs. And we get then also, of course, compounds which are causing DNA damage, and all this together is actually causing many of the observed health effects. But in detail, of course, it's still a lot of research. And also for the small particles, it has been shown that the particles actually can enter; they can penetrate through the barrier, and they can enter into the blood stream and then also do harm there. If we now look very briefly on a human cell, it's understandable, it's a very complex system, of course, but it's understandable that the particulate matter can either be acting via receptors, or normally it's taken up. And this engulfing more or less of the particles into lysosomes very often is rupturing. So the lysosome ruptures, and the particle content is coming into the cytosol, and then there is an activation of let's say, inflammatory process, which in the end kicks off interleukin-1 alpha and beta formation, and this is more or less bringing up the whole biological process. So you can see a close-up figure of this process, which is actually then causing this interleukin alpha 1, alpha and beta. You can see the alpha and the beta, And this is more or less an sterile inflammation. So it causes all the other cells to be alarmed of infections which are not there. And then you have this chronic inflammation, which is also responsible for many of the health effects. Okay. And one important aspect we will see later when we come to single particle mass spectrometry is, of course, it does matter if how the internal and external mixture of the pollutants on the particles is. Because when we have particles which have only a small contribution or fraction of a toxic component, the cells may still cope with this. But when we have particles which have a high concentration of this pollutant, this could be actually overwhelming the defense and then trigger this inflammation more efficiently. So on the same total dose, the mixing state also plays an important aspect for health. Okay, but if we now would like to measure it, of course, biological things we can only measure with chemical methods indirectly. We can measure soot, pHs, and so on. But for this, it would be very helpful to also look on the biological systems by itself. And there's a method which is called air liquid interface exposure of human lung cells, which can be used for this approach. So the idea is that cells are actually grown on a membrane, lung cells, in a way that the cells can be exposed to air, like in the lung, and they are nourished from the medium from the bottom. And there are different cell lines, so alveolar and bronchial cell lines, which can be used for this. And these cells can then be exposed to aerosols. And this is mimicking, of course, a situation in the lung very well. And then we can use all the biological technologies we have to look how the cells are reacting on different aerosols or pollutants. So for this, actually, in many cases, we are using even two cell lines, so very similar, like in the human body, we have a cell line for epithelium, which is the cell line which is in air contact, and the other cell line, which is on the side of the body, which is more or less towards the blood vessel, is the endothelium. And so we have both cell lines actually on both sides of the inserts, and then we can use this approach to look at the human lung cells. Once more, you see how we simulate the situation now in the lung. And then we are using this type of exposure stations. These are instruments which allow to control the aerosol, which could be sampled from the ambient or from emission sources, which are then brought to the right temperature and moisture, so diluted, and then the aerosol is flowing over the cells. And this can be done, for example, here it's a measurement campaign quite a time ago we did for ship engine emissions. Yeah. And you can see here how it looks like. Well, you can't see because the video is not transferred. In my computer, I could show you next time. Sorry for this. Yeah. Okay, so and one study we did with this technology was to look at secondary organic aerosols. So if you look at the organic aerosols, actually, the majority of the secondary or the majority of the organic aerosol is secondary. The primary aerosol is much lower. So gas phase components are actually transferred into less volatile species. We have oxidized species. And the question is, well, is this secondary aerosol as toxic as a primary organic aerosol? And for this question, we built an experiment. In this case, we are using a standard aerosol generator, and then we use an oxidation system. It's a PEM in this case. And we give precursor. So either we are giving naphthalene, a typical anthropogenic precursor from combustion, or beta-pinene, a typical biogenic precursor to it. And then in the end, we get the soot actually is quite, it's very lean soot. There are not much chemicals on it. So what we are doing then, we get like soot droplets. Yes. Okay. Sorry. Okay. Good. So we get the soot as droplets covered with the SOA. So the SOA is more or less on the soot course. And then we look on the liquid interface cell exposure with the system. We also looked at the chemistry. Interestingly, we only have one precursor compound here, and we can see a huge amount of aromatic species which are oxidized for the naphthalene in the SOA, and a huge amount of aliphatic oxidized species from the beta-pinene. So it's chemically quite different, albeit the concentration of secondary organic aerosol is very similar. So chemistry is different, but the general properties and the amount is very similar. And if we then look to the toxicity, now it's a bit difficult to read. This is a clean air and then the dilution. And we look, for example, at cell viability or inflammatory response. And we always have in blue, we have the beta-pinene, which is the biological, and we have in purple, we have the naphthalene, which is the anthropogenic. And what we see actually is that always the anthropogenic aerosol or precursors are more toxic than the biogenic. So the biogenic aerosol, so oxidation per se, seems not to be the reason. It depends if it's aromatic, coming from combustion, traffic emissions, or if it's aliphatic, different structures, and it's much less toxic. And we observed this also for many other tests. For example, for gene toxicity, we looked here at the DNA strand breaks, and we could see that we have also here we have for naphthalene a much higher activity. Interestingly, we have even seen a secondary gene toxicity for naphthalene only, naphthalene SOA, meaning that also the inner cell line was actually genetically unstable. So it's the first step of going systemic. So to conclude here, this secondary organic aerosols have different potency for health effects depending if they are anthropogenic or biogenic. Then we also looked at real emissions, like from a car. Now we used a car or wood combustion. Now we use a different type of measurement system. It's a flow tube reactor. It's a peer reactor developed in University of Eastern Finland. You can see it here. It's quite much bigger. It's 2 meters long. And we have here the car on a dynamometer or a wood combustion. It's aged. Here we have the cell exposure. And we do, of course, all the characterization with AMS and so on. But I will not go too much into it. But I would like to show some of the results from this behavior. So the interesting point is this is a Euro 6 car, and we don't have to look at all the graphs, but this is the particle concentration, and you see for blue now is the fresh and red is the aged. We have no particles at all because the particle filter is taking all away for fresh. During aging, however, we have new formation of particles. So we get a huge amount of particle mass and also numbers here due to the aging process. So the PTR shows us that then a large amount of oxidized gases, for example, are present here. So particles are actually reformed after the emission in the sunlight, which is quite important, in particular here also in India, because you have so strong solar irradiation and so much emission of gases as well. If we now look to to toxicity, we can see that fresh and aged, so this is the metabolic activity, or here cytotox is fresh and aged, that actually this aging brings back the toxicity. So the filter is taking out the particles, but new particles are formed and they are again toxic. And this we have seen with many different assays. I will not go in more detail. It was just last year published in Science Advances. But the whole message is that these particle filters are not helping when the gas phase is actually atmospherically transformed and forming secondary organic aerosols. And we did the same study concept also for wood combustion. In wood combustion, of course, we don't have any filters. And what we can see here is a very variable type of combustion, always putting new logs on. And what we can see is that some of the pollutants are actually transformed. So we get more during aging. We are getting more hydroxy PAHs, for example, and less PAHs. It's about 2 hours, 2 days of aging in general. And if we now look again to toxicity, we see that with aging, it's increasing. It's the toxicity of the fresh, and if we age it short and longer, it's getting to be more toxic. So also here, even if we have primary particles, the additional aging is toxifying the particles. So this is an important aspect to consider. So we also did studies with animals. So we looked here at for example, mice, which have been exposed to wood combustion, fresh and aged. And what we can see here is that neutrophil cells are actually attracted. So it's a strong inflammatory marker. And we also see more DNA strand breaks with aged emissions in the lung alveolar lung fluid, which has been taken out. Yeah, so furthermore, looked at the genetic reading. I will not go into much detail here, but it turned out that the macrophages are actually polarized, so they are going in the direction of, let's say, anti-inflammatory activation. So they are trying to let's say, react on the stress. And we also looked at murine macrophages, so also from mice, cell line in the same experiment, and we could see also here more toxicity in case of the aged case. And then we see similar activation of pathways like in the animal. And this shows us that the cell tests are giving the correct information, same information for animals, for human lung cells. So it's most likely for us humans, it's the same. Okay, so with this, I will leave the biological field and I will come to our 2 measurement techniques. First, short aspect before I come to single particle mass spectrometry is a coupling of thermal analysis combined with photo ionization. So it's a classical ECOC analyzer. I think you have it probably here as well. And the ECOC analyzer, of course, is digesting all the compounds to measure the carbon. But if you take a small fraction before in the mass spectrometer, you can get fingerprints and better understand what the sources are. So for this, what Photonion did, it's our spin-off company. So I'm not the CEO of Photonion, but my former students are running the company and make their living. So they develop online process and combustion monitors, thermoanalysis coupled with photo ionization, and then this hyphenated system for aerosol thermal optical carbon measurement with mass spectrometry, underwater mass spectrometers, and also the single particle mass spectrometer. I think underwater and water monitoring is not the topic which is so interesting for you here. But we will start now to discuss a little bit here on the two systems. And first, it will be the coupling of the EC-OC analyzer with photo ionization mass spectrometry. So photo ionization mass spectrometry, you work with PTR here, and similar as PTR, we have a soft ionization method. And the softness is coming from the reduction of the energy we are supplying either by VOV light, so 180 nanometers is 10.5 EV, which is just slightly above the ionization energy, so you will not fragment. Another possibility is the ramping method, where we use UV light, but intense laser pulses. And if compounds which are absorbing, like aromatic species, they can be ionized by a two-photon ionization process. And of course, PTR is extremely sensitive because you have high pressure ionization. You sometimes have difficulties with ion molecule reactions, cluster formation, and so on. This all you don't have with photo ionization. So when we look, for example, for process gases, we get fingerprints, and all the masses are then molecular information, and this is used in many projects for online monitoring of industrial processes or coffee roasting exhaust or cigarette smoke, puff by puff, and so on. But the interesting point is you can online get information, soft ionization information from the gas phase, which is evolving. And when we now look to an EC-OC analyzer, and we are working here with the colleagues in Slovenia on the DRI system, actually also with Judy Chow from US, where we developed it. But the colleagues in Slovenia are developing now this commercial instrument, and with European Union funding, we were able to make a combination of the two instruments. So a small fraction, actually, when you have the EC-OC measurement, you can do optical measurement in the same time, brown carbon and black carbon measurement if you have a multiple laser array here, and so on. And in the same time, you are measuring during different temperature steps the evolvement of carbonaceous compounds. All the carbonaceous compounds are transferred into CO2, and the CO2 is measured with NDIR. But before we destroy it, we take a small fraction, about 5% of the flow. We take in the mass spectrometer and we look what's coming out of it. And you can see here the coupling, like this one project Photonion did together with them actually in China. So it's the EC analyzer and the Photonion mass spectrometer. And what you can see now when we are doing these measurements, you can see during the OC1 and OC2 measurement, you get see the fingerprints. There's no ramping. Now we see only the aromatic compounds. You can see the fingerprints of the evolvement of the different compounds during this measurement. And then you can later on look on the fingerprinting. And of course, with the ramping technique, we only see the aromatics, which we always like, because the aromatics are for health effects very important. So just to show you the information we get from such a 2D figure we have seen before, we get on the one hand, up again. Yeah, we can get for OC1, OC2, OC3, we can see the fingerprints. And then we see the desorption phase of pHs. With higher temperature, it moves to larger pHs, and we see also pyrolysis products. And for OC3, we see mainly decomposition of polymeric matrices. So we can see more or less quite nicely what is actually molecular composition and what is pyrolyzed what is, let's say, oligomers or polymers in the aerosol. And depending on that, we can also see that for pyrolysis, one example here is when you look at phenol, for example, is a small aromatic compound. It comes only from OC3. It's a pure pyrolysis product of oxidized SOA. While other compounds, like, for example, here's the aromatics, the four-ring aromatics are coming mainly as desorption peaks. So they are mainly molecular species which are just vaporized by thermal desorption. And this we can see in the thermogram. And then, of course, we have for different sources, we have a different fingerprint, and this information is always recorded during the ECOC measurement. I will not go too much into detail, but you can see here also, we can measure in parallel SPI and REMPI, and we see here for wood combustion and for diesel, we see specific markers. And if we do it kind of harder, so a bit of impact ionization as well, we can see the same masses we have in AMS as well in the same time from the sample. And also different wood types, for example, you can distinguish. We have here for birch, we have the betulines as markers, which are only in birch wood and spruce wood and beech wood. You can see that here in the phenols there is a different marker because we have soft and hard wood which have different phenolic constitution. And you can use it for this discrimination, of course, and different sources as well. And what's also interesting is you can use the optical measurement. Now this is for ship aerosols. We can see the radiative forcing is more or less the absorption, the light absorbing capacity, which is integrated over the whole wavelength range. And we see, for example, that the high viscous fuels are making much more radiative forcing by absorption. On the other hand, for the climate effect, it's very important to consider the new formation of clouds, which is a different effect, which we cannot measure, of course, from a filter sample. Okay, but finally, we will come now to the last part, which is the single particle mass spectrometer we have developed. It's actually that what we are mainly doing in the moment. So it's our main research topic currently in the group in Rostock. And the aerosol mixing state, of course, for you, this is very clear. You are expert in that field. But the mixing state is very important for many effects. And if we just take a very simple case, internal mixture, external mixture of an organic compound and a polar salt. Yeah? So we can have, of course, a perfect external mixture or a perfect internal mixture. And this, of course, is now different activities, for example, for cloud condensation activation. So if we take the internal mixture of ammonium sulfide and a hydrophobic organic compound, they will be all active for cloud condensation. If we have an external mixture, only 3. If we have a real world mixture, maybe only 4. So there's a direct link between mixing state and the formation of cloud condensation nuclei. It's very much known in the climate community. And you can see it here. We discussed before the absorption of ship emission particles, but here you can see that ship emission particles also can act as cloud nuclei. And this is, of course, very strongly increasing the albedo. And here we have a reduced, let's say, or we have a shield. Now with stopping to use sulfur fuel, we we are heating up our oceans even more. So it's maybe it was a wrong decision to take out this sulfur for the ocean-going ships. As mentioned before, we have the same aspect also for external and internal mixed pollutants. So if we have pollutants with a very high concentration of intoxicants, single cells are very much affected and the inflammation is very much boosted. If it's distributed to a small amount in each particle, it's much less harmful. But we have up to now, no good measurement techniques of this except for online measurement, single particle mass spectrometry. And that's actually the field we are in with the group since 20 years or so. But we haven't invented this. So this has been done mainly, we have to say, by Friedlander and Spengler. They did the first full functional single particle mass spectrometer. Prasa then added the two mass spectrometers that we can both polarities, albeit the idea was coming from Spengler. And then there are quite some groups which are using it, and we as well, but we have, of course, our own vision and we modified it quite a bit in the last years. And this I will show you in the following. So what we get typically are single mass spectra like this. This is a single spectrum of a wood combustion in ambient air, strong potassium, organic fragments. It's aged. We have nitrate, sulfate, oxalate we see here. But of course, we are measuring thousands of particles. And then when you would like to make, for example, a quantification that's nicely shown by Rob Healy, you can, of course, stagger this with the response factor, nitrate, sulfate, ammonium, and the elemental carbon, which we also see in single particle mass spectrometer. And of course, if we have dust, we see also the dust constituents. So this is possible, but of course, our aim is to make it more towards health. Let's say health impact relevant, and also to make it from our initial instrument to something which is also of interest for other researchers. And Johannes Passig, actually, is my group leader for the single particle mass spectrometry. Maybe somebody has seen him already on a conference or so. He is a physicist, a laser physicist, and he has actually brought in some very good ideas in the last time. So the first idea was to enhance the detection of metal. So it was around the technology, but very important for climate and for health is iron. And the question is, can we enhance the detection of iron in the particles? And there's actually a possibility. And the possibility is if we have a laser which is in resonance with iron, then we can enhance the detection of iron quite a bit. And iron is very important. It makes a lot of stress in the lungs, but it's also important as micronutrition for the oceans. So it's very important to measure iron. So we are using an approach we call pumping iron. Yeah. So we take a krypton fluoride laser to pump the transition. It's another pumping iron, but we don't do that. Yeah. So we pump iron only with a laser. And what we get is actually here we use the tunable laser. If we hit the iron resonance, we get a factor of 5 or so increased detection of iron. And as iron is very ubiquitous in aerosols, all the other transition metals are also more sensitively detected. So when we now look at the ambient air in remote places, oops, this was wrong. Now we have to. Can I go back? Can you just? Can I do it or can you do it? So just click on it. Yeah. Okay. Thank you very much. So when we look to the iron-containing particles, we see that mainly they are, let's say, emission type of particles, but some And this blue one here are actually pure particles from sea spray with iron. And there, the iron must have been some biological origin. So it's actually quite nice, nice result, which was published here in chemistry. Of course, the metal detection also can be used to look at emission sources. We are at the Baltic Sea. In the Baltic Sea, we have ships which are using heavy fuel oil still with scrubbers. And when the wind now is coming from the Baltic Sea, so we are about 30 kilometers inland. We are away from the oceans. But then we can see single ship plumes of ships passing by using this heavy fuel oil, because we have here vanadium and iron particles which are very sensitively detected. And we also use this for more studies on ship emissions. You can see here we are using our single particle mass spectrometer in a field campaign on a ship, on a German research vessel. And we checked for different emission profiles from ships. And at the same time, we also looked in a European Union project. We looked from this ship. Actually, we looked with a blimp from Prague University to directly sample and compare the samples we have taken with mass spectrometry and the samples we were taking here directly from the ships by using this blimp. And here you can see how the ship is coming back. The airship is coming back to our research vessel, and we could then collect the samples. As I mentioned, for the marine science, of course, it's very important to look in the ocean how different elements are transported. I discussed that iron is very important for algae growth and also for climate. In fact, so we used here this research vessel. You can see our mass spectrometer here, and it's operating, and it was a transect from Africa to Australia in the Indian Ocean. And actually, what we looked at now, Joe, we are still in the data analysis, but just look on two different stations we looked at, and you could see how the distribution of the particles are. Interestingly, we see a lot of sea salt, of course, sea spray, but we also see dust long-range transport, which is an important. Just click to some interesting particle classes here. We have aged sea spray, which is quite interesting because there are not so many nitrate sources in this area. So this must be from lightning because there is no emission. We are really on the open ocean here. And we see more aged and more nitrate we actually assumed. This was quite surprising. And of course, we see biological activity. So we have MSA containing particles. So even in that very remote areas which have low productivity, we can monitor the amount of those components. And then we have mineral transport. You could see this is laterite soil, which is coming like the red rocks, Ayers rock from Australia. You can see a strong iron signal. We also have the magnesium and calcium containing dust particles here. And all this we could see. So you could see that the metals, and enhancing the metals is really helping for single particle mass spectrometry. But the next step for us is we want to learn more about the organics. And for the organics, actually, for us, the pHs are very important. Why? But firstly, they are very important as compounds which are health relevant. Secondly, they are an organic compound class which is tracing or which is showing us how the oxidation of this organic material is going on. And this I will show you in the following. But first about the measurement principle. And this was an idea actually of Johannes. So what we are doing, we first have to desorb the particles. And then we are ionizing the plume automatically with a laser to doing the measurement of the dissolved pHs. But as we also want to see the metals, we have a back reflection. And the back reflection then is doing the LDI process for the elements. So we can do both ionization at the same time for the same particle. And this was something new. We had before different laser approaches, but only with this trick we can do it automatically. And to show you how it works, I have here an animation. You can see the particles are entering the aerodynamic lens. And then they are coming into the scattering unit. And if they are scattered, they are getting, you get the information on the size. And when they reach the ion source, then the infrared laser is heating up. pHs and other compounds are dissolved, ionized, and then the back reflection is doing the measurement of the metals. Then we have the metal ions and the pH ions, which are then separated in the time of flight mass spectrometer. And we have both channels, and you can see that we have the classical single particle mass spectrometry information here, which is enhanced in metals. But now we also see the single particle pH fingerprint of that particle. And this is something which is really new. You can see, for example, the typical particles from diesel soot or wood or tar ball, yeah, and we can see the pHs, we see the metals and also the soot, of course, which making carbon clusters. And when we maybe quickly go back to the ships before I will tell something about wood combustion. For the ships, actually, we had one issue, because when the ships are using clean fuel, we are losing the markers for detecting the ships, because no vanadium, little iron. But when we look at emissions here at the ship engine, we see interesting particle spectra. We see that the negative, or we see that the classical single particle mass spectrometers show a very much externally mixed pattern. So we have like soot particles, and we have particles which have mainly calcium in it, is coming from the oil, and so on. So they are very different. When we look now to the pH pattern, they're all the same. All ship particles of one engine have the same pattern. Why is it so? Because the soot is first formed, and then the organics are condensing on it. And the organics are from the fuel or generated, and they're all condensing in the same manner. That means that this information of the fuel is imprinted on the particles upon emission. It was a nice finding. So with this, we could see this as a source marker as well. And when we have different fuels, we can see we have different distribution of the pHs. So we have this very, let's say, steep decay for distillated fuel, and we have this more or less more Gaussian form of pHs emitted from heavy fuel oils. Yeah? And we have shown that with different fuels, of course, you cannot do it with a single particle, but during a plume, you measure hundreds of particles, then you can pinpoint if it's a heavy fuel oil or light fuel oil. This is, for example, shown in the previous slide. So when we now look to a very remote area, here in Sweden Island, and we look to the particles, so we have here taken about 1.3 million particles in a really very clean air. And we see a lot of different particle cores. Yeah? So it's sea salt, of course, but it's also dust particles, iron containing, it's mainly organic. And the outer ring is enlarged by a factor of 10. Notice that. Is the particles which are containing the pHs. What does it mean? The pHs are really concentrated on very low amount of particles, and this makes an external mixture for the pHs, and the concentration for some particles are very high. And this is actually one of the reasons why we assume that the health effects are still so high in Europe, albeit the concentration are so much lower, because we have still these high toxic particles in there. And we could see them now with a single particle mass spectrometer. You can see here, for example, these are a PRH pattern where you have just the bare skeleton. This is very high temperature combustion coming from coal power plants in Poland. Here we have a wood combustion, pyrolysis particle, and so on. So, and as I mentioned before, we had then a seldom visitor on the island, which was a ferry. And you can see here the ferry is coming by. We see the particles, and actually, indeed, it's a ferry running on this classical fuel without vanadium, and we could measure it from that on. Okay, so one aspect is that in the Baltic Sea, they try to minimize the emission by sulfur scrubbers. Sulfur scrubbers, and the sulfur scrubbers actually are not. Okay, sulfur scrubbers. I cannot move forward now. Cannot works. Sulfur scrubbers. They are actually not changing the small particles, not the pHs. So they are cleaning the sulfur, but we still have the health relevant particles here. So in this respect, we could identify that scrubbers are actually not doing what they do. They are not reducing the health risk of the emissions. Okay. Now, the last example is a wood combustion and biomass combustion. So wildfire are, of course, a very important source, and also biomass burning in India is an important source. And when we look to biomass burning, we have actually on the one hand, direct emission of, let's say, aromatic compound, pHs, but we also have a lot of direct emission of polar compounds. In the photochemical transformations, then we have further, let's say, change of the polar compounds forming oxalate, which is more or less the end product of the aging. So it's quite complex. But we have a balance of these oxidized and non-oxidized species. And I will now focus here on the boreal wildfire. Boreal wildfire emission, yeah, and you can see here the simulation of a wildfire is an open burning put to a chamber, oxidation chamber, and then we are looking at the different particle classes. And the single particle mass spectrometry, we see four main classes. It's nitrated or nitrogen-containing particles. It's more or less alkylated pHs. It's something like a tar ball, huge amount of different organic fragments, and the classical pH pattern. And we can see when we put on the light that we have a strong and a quick change of these particle patterns. And in this study, we were mainly interested in the climate activation of the particles. So we could see here that the kappa value is increasing. That means we have an increasing, let's say, cloud condensation formation for some of the fires, but we have seen for some of the materials we don't see it. And the question is why? And you could see here different chemicals and now single particle data. You could see when we have, for example, a view on this mixing right ahead, right away. So if we now look to this kappa value, and if we look here for some of the boreal forest particles, we see actually increased kappa with aging. And this makes sense. We have more polar compounds which are formed, more hygroscopy, and we get more water activation, higher CCN activity. But when we look to the savanna type of aerosols, what's the opposite? It's getting more polar with the organics, but we see on the other hand that we have less kappa value. And we had a big problem. But we could solve the problem because savanna wood has a high potassium content. And the potassium chloride, which is formed, is very hygroscopic. And this is sulfatized during the aging. And so the inorganic change from potassium chloride to potassium sulfate actually is reducing the kappa more than we gain by the oxidation of the organic. So we have to look on both sides, on the inorganic and the organic, to understand the activation of the particle. Shown here again, you can see that we have here this change in savanna against boreal forest. We have here the potassium sulfate coming up very strongly. Yes, let's now look a bit deeper into the boreal forest data, because the interesting point actually what we know, and if we discuss now with the aerosol scientists in the US and Europe, what people want to know is how the particle structure is. Do we have a core or shell structure, and how the oxidation happens? And we looked in our data for this. An interesting aspect is if we change the humidity of our experiments. So either we have RH, so very dry, so no moisture, up to 80% relatively humidity. And if we now look the decay, so the oxidation here of the aromatics, it means how much particle mass actually is getting into contact with the OH radical and is oxidized. We can see that it's a much longer survival time under dry atmosphere compared to moist atmosphere. And this, the reason for this is that we have, let's say, we have a particle which is mainly a core, which is diffusion limited, which is nearly solid. And there is actually little possibility of the OH radicals to go into the particle and oxidize the organic compound. When we have high humidity, actually we are getting a big increase anyway of oxalate, but it's actually much higher, or it's higher the more water we have in the air, because we are getting, let's say, more a liquid layer, a liquid shell on the particles, and then the liquid shell can better transport the OH radicals to the core, and we have a stronger oxidation of it. So, and this is actually quite something quite new, that we can look in the formation of the core and the shell structure during the oxidation of the particles, which is possible as we see the information of the polar and the non-polar compounds at the same time. And this is a currently very much discussed aspect, yeah, that's, and it might be that the humidity is the missing link why we see so different CCN activation results from different wildfire events, yeah. So in the end, when the air is coming after 1,000 kilometers somewhere, it's not so easy to find or to predict how the CCN activity is. And this might be the missing link, that we have this core shell activation here playing a role. Okay, so this brings me to the last slide. Again, you can see here for the three moistures, dry 50%, 80% RH. And you can see that that's a structure. Now we have here, we have it oxalate rethene, versus PAHs and methylglyoxal. And again, we can see here how it's changing when we are looking only in these compounds during the chamber experiment. But if we look at now for the different humidity, this is now again for 50%. You can see that in the end, the moisture is giving a different picture, a different distribution of the internal external mixture of the components. So it plays a very important role. With this, I would like to thank you. I will first make an independent summary for single particle mass spectrometry. I have shown you that you can address the chemical composition, that you have the possibility then to look at the internal external mixing state of toxicants and compounds important for CCN activity. I've shown you the trick with the iron enhancement, which helps us in general to look at dust particles and also to look at the iron uptake of the oceans, and also for health effect is quite important. At the same time, we could add the resonance, and it's now automatically added in the system to detect single particle PAHs. So the PAH pattern gives us a view into the molecular organics. And this allows us in the end, in the wildfire experiment, for example, which I've shown you, to look at the salts, the organic molecules, and also the oxidative products in the same time. And now we can better understand the structure of the particles and how this is changing. Outlook is, of course, different further emission experiments. In the moment, we are working also again with ship emissions and new fuels, and also aircraft emissions with single particle mass. Marine and polar aerosol studies. I've shown you a little bit from these cruises we did. In the moment, one of the customers of Photonio are doing measurements in Spitzbergen for Arctic haze, because they want to see if the Arctic haze phenomenon has to do with organic compounds, which are then going, well, which are increasing in Arctic spring and make Arctic haze formation. I've shown you that the health impact is a quite important aspect here, and we are setting up some studies there with more toxicological, let's say, workforce together with SPMS. And we also have lots of applications for security and safety. You could detect explosives. You could detect, for example, drugs. And we have also shown that we can use it to get drugs detected from different packages in DHL. And we were able to measure there at the DHL hub. It's a big German company, and they have a 1 kilometer long building. And we were able to find cocaine and other drugs in the packages with the single particle mass spectrometry. So in general, the whole summary is, I think online is important. Everything, if you want to learn new things, we have to go online. We also do offline, very important, but online is important. I've shown you an online measurement technique for biological effects with the cell exposure. I've shown you, well, it's offline, but we do online during the TOCA measurements. We can also measure the chemical information from that. In the end, it gives us some data like AMS, but also fingerprinting for sources. And I've shown you the new Photo Ionization Mass Spectrometer, which gives you online information on organics, elements, soot, and classical parameters and size distribution. And with this, I thank you for the audience. This is the working group. We have to make a new photo. A bit old in Rostock. And of course, funding, it's coming a lot by German Science Foundation and European Union. And yeah, so with this, I'm at the end. And if you have any questions, we can discuss further. Thank you very much.
Thank you, Professor Ralf. It was a very wonderful talk and enlightening as well. So actually, I have a couple of questions. So regarding your initial results now that you have shown regarding this viability and others. So you have shown that you have used PAM for doing this extreme oxidation and then exposure analysis with the cells. So what kind of aging scale that you have utilized?
It was photochemical aging with ozone and UV light,
Mhm.
and about 2 days photochemical age. So we use butanol with PTR
Mhm.
to measure the photochemical age, and it was about 2 days photochemical age.
So do you do any like sensitivity studies of like varying the aging scale, how it is?
Yes, of course. The problem with the biological measurements is that you need for each exposure 4 hours, and you need 3 to 5 replicates. So it's a huge amount of time. So it's a limiting factor actually for this is if you have many sources, very often we are able in a 2-week measurement campaign only to do a very limited set. So for the wood
Hello.
combustion, we
Yeah,
have
sir.
different ages.
Scrap, no, sir, it is not with me. I will check, sir. Just give me 2 minutes.
No issue.
Yeah.
Hello?
Mhm.
Yeah.
Okay.
Okay.
Yeah.
You make a second.
Okay.
Sachin.
Mhm.
Hello. I have another question. Like how quantitative PIMS is in terms of like quantifying VOCs? You have shown a lot of VOCs that can be measured.
Okay, for a single particle mass
सर
spectrometry.
अभी अभी हमने जो कम्युनिकेशन किया वो तो सिर्फ मेल थ्रू ही किया है उनसे. We have not initiated any e-office file for this.
Where is that?
Madam is calling.
इधर से म्यूट नहीं कर सकता.
Oh, I don't know what to answer now. Okay, I can start. So of course, you cannot quantify the information for one single particle. You do it like with the AMS. You have a standard and then you quantify over, let's say, several hundred particles, and then you get an information which is similar for the AMS. For the pH, it is like a pH factor you are quantifying because you cannot work it out for the individual compounds. You have like the pH class, and you associate this according to a standard measurements, and then you give a value of the pH class.
Because actually getting pH into like effectively into the like inlet as a like maybe like in gaseous form or in a particulate form, it's very difficult.
Yeah. But of course, here we have an aerodynamic lens, and these particles normally, which have combustion, let's say, history, this pHs are bound on the soot matrix, and then there's a layer of oxalate around it, so they will not be in the gas phase. So in the aerodynamic lens, the gas phase is more or less stripped off, and we see here only the particle phase pHs. So this is only particle phase pHs we see.
Understood, but only to calibrate it. Like
So we have not done yet a full calibration. Actually, it's on our list. But then you would go with a standard solution with a given amount of particles, you spray it, and you have to compare it with a filter measurement as well. And then you can take your overall sample signal over several hundred particles, and then you have your value for it.
Okay.
But we can discuss it also in more detail later. Yeah. But it's definitely, in principle, the approach is very much straightforward to that what you do with the AMS. The AMS everything is due to the ammonium nitrate mass. Of course, you need then to have different standards for the different compounds.
And they extrapolate it for like relative ionization efficiency for other
Yes,
components as well.
yes, correct.
So just last question. So you have used VUVs for ionizing.
Yes.
Are you using any targeted molecule for ionization or it's just simple ionization?
For the VUV, the issue is a bit a longer story. So with a VUV lamp, it's more or less it's ionizing everything. But you have different cross sections for different compound classes. So aromatics are typically a factor of 20 higher than aliphatics. And so that's why PTR is so sensitive, because you are ionizing at high pressure. We are ionizing at low pressure, so it's mainly good. The VUV ionization is mainly good for higher concentrations like emissions. So for ambient, it's a kind of difficult. With the ramp ionization, however, on the other side, the sensitivity is so much higher, even higher than with PTR, that you can overcome the lower pressure. So it's rampy aromatics are super sensitive.
Regarding the dust analysis using the SPMS, so is there any assumptions? Because that matrix of dust is super complex to break. And
Yeah. So with the dust, there is one issue. So we are seeing mainly the positive elements. So we don't see the silicate so well. This is just a question of the laser wavelengths, and we wanted to have the speed compromise to look at iron, the elements, the organics, nitrate, sulfate, everything. If we would like to break it down, we have to go to a very much shorter wavelengths, and you see more information on the silicates as well, but you are losing the information on the other elements. So, but can be done. Yeah, can be done. But it's I think for dust, it's relatively well established. So dust measurement you can do quite well with single particle mass spectrometry. So it's there are also, you know, from the other authors who started with it, even from Spengler, there are nice papers out, and then Dan Murphy is doing quite a bit for dust as well. And this system in principle can do the same. It's just a question which wavelengths you are taking. But the trick is to combine everything, that you see the polar, non-polar organics and the elements, as well as soot, nitrate, sulfate. That's maybe as a nice addition here. But of course, if you are specifically interested in dust, we can go to a different laser wavelengths, which is really maybe then giving you better information.
aerodynamic lens has a different cutoff. Aerodynamic lens has a different cutoff.
Yeah, so the cutoff of the, well, it's more or less a classic one. What I have not said, so the sizing is working down to 200 nanometers. When we have very small particles or emission particles, typically we go for free running. So then the laser is going with a very high frequency up to 150 hertz. And we are just taking the particle hit as they come. Then you can measure down to 50 nanometers. But you don't have the full size information. You can only say it's a particle which is giving no scattering signal, so below 200, but this and that chemical information. So for full sizing, it's going up to a bit more than 1 micrometer. But there's also an aerodynamic lens system, which is more on the larger side. We are currently cooperating with some colleagues who want to make a really broadband aerodynamic lens. But up to now, it seems that the compromise is working not so super well. So you can get it a bit more extended to the lower end and higher end, but the overall transmission is going down then. So, but normally, if you are then interested in the bigger particles, probably you would go for a different type of aerodynamic lens. It has a cutoff, lower cutoff than of 300 something. You still will see them from time to time, but just the hit rate is much lower for the small particles. And normally, all the people try to get more in the lower range, but there are both options available. But it's very similar to AMS, by the way. So it's you have the same thing.
Regarding that ECOC that you connected with mass spectra, you also gave that in OP or EC1 flexometer the signals? I mean, EC.
Yeah, with EC, very little signals, very little organics. So with EC, then you give the oxygen in, and I think everything is readily oxidized already. Of course, what you can do is you can, if we do impact ionization, we see already then quite high signal of CO2, but not much organics.
Like sharing pyrolyzed carbon, can we see any signals during that?
No. So because we see only the gas phase components, yeah. So only what is coming out, and we see that in the moment you switch to OC. To EC from OC, you add oxygen to it. And then at these high temperatures, oxygen, you will not see organic compounds anymore.
And there is some correction.
Yeah, but the correction you are doing via the optical measurement. So you have like in the classical DRI, you are measuring the charring, and you are going back to the original value, and then you are counting this CO2 you are measuring. You are counting still to organic, the charring part, but this has nothing to do with the chemical measurement, because when we start with the oxygen, we don't see any organics anymore. Just too hot and oxygen, everything is burning.
Sharing, they are saying like it is part of organic, but it is like
but
you might see like whether we see.
Yeah, I got your point, but it's
that is basically with the OCC itself, like the OCC instrument, the sharing in.
yes.
What he talked about connecting photo ionization mass spectrometer to see the fractions of organic carbon, like OC1, OC2, OC4, and then you have different fingerprinting at different carbon fractions. So that is the advantage here with PIMs, MS.
So EC is prohibited.
Pyrolyzed carbon is also part of organic carbon, right?
Yes, but
Any mass spectra during that period.
no, but then you have to stop.
Few of that part.
If you want to resist, you have to stop your ECOC measurement at that point, and you have to take your sample and look with MALDI. But these are still polymeric, these are not molecules, they're still polymeric things. And if organics are coming out in the EC mode and you have the high temperature and oxygen, they directly oxidize. They make CO2. You will not see in the mass spec anything. Yeah. So oxygen, in the moment you are in the EC mode, organic measurement is over.
It's also because like in organics, we are heating to up to 550. So
Yes.
the possibility of sharing actually comes up, and that's why we have to subtract that from the EC. So
Yeah. But of course, it's also kind of artificial. It's a definition.
Yeah.
Because OC and EC is a simplifying thing. You know, you have all the oligomeric, and the oligomeric structure is changing. So when you, for example, do the same experiment slower or faster, so faster heating or slower heating, your steps will change, because you have chemical reorientation, and also the molecules you will see will change, because you have more or less a tempering of your organic material, and different species will come out. So it's a very simplistic concept to split it, which has normally you would need to define something like organic, oligomeric, polymeric fraction, And at some point, EC, well, you know, if you look into EC and look, stop, take it out and put it into the EDX, you will still find oxygen in there, yeah, and other elements. So it's not 100% EC. It's just definition. Yeah. But with a mass spec, in this case, we cannot help because in the moment we put on the oxygen, it's gone.
If no more questions are there, then let us thank Professor Zimmerman.
Okay, thank you for having me. Thank you.